In the next few videos, we're going to take a look at some methods for reducing the execution path length. And so recall here what we're trying to do is we're trying to reduce the number of micro instructions needed to carry out some ISA level instruction. So the first of these techniques we're going to look at is just merging our main1 sequence, which we saw was just one line, and the book refers to that main1 as our interpreter loop. We're going to merge that into the end of each microcode sequence. And what we're going to see is this actually only helps us in a specific case of when we have dead cycles in a certain sequence. And so what a dead cycle is just some time when our ALU is not being used. And so as we can see, we're going to look at our pop instruction sequence here in a little bit, but basically our dead cycle is going to be this space here where we're not doing anything during pop 2. And of course the reason for our dead cycles is because we're having to wait for some read or we're having to wait for some write before we can move on and do anything else useful. So the cost for doing this, of course, is if we add this main1, if we merge this to the end of each microcode sequence, now we have to be taking more space in our control store as opposed to if we just had main1 in one place and we're referring back to that go-to main1 at the end of each microcode sequence. This is a little bit different than what we talked about in the previous video. So in the previous video, we had talked about how our 4 to 16 decoder decreased the word size in our control store. So here, what we're talking about would really be number of words, right? So we still have the same word size. So maybe our microcode wasn't filling up the control store fully anyway, so essentially in that case, it doesn't really cost us anything. But again, it depends on the specific situation. And so what we can see is if we look closer at this pop instruction, and so let me just leave this first one on the screen here. So again, we've got this dead cycle where we're not doing anything, and so we can merge our main1 at the end of it. But of course what we could do if we want to improve our speed is we can take this main1 and we can move this up in this spot where nothing else is being done. And the reason for that is of course our read and our fetch are independent, right? One, the read is happening with our MAR and MDR registers, whereas our fetch is using our PC and our MBR register. So what we can do then is we can rearrange that and we can move our main1 to the dead cycle as shown here. So this is main1.pop, and so we see it's still just PC equals PC plus 1, and we're initiating a fetch. And then we don't actually do that go-to. We keep that down at the end of pop 3 because we want to finish what we were doing in pop 3. So we sort of split up the main a little bit, but the main thing is that we are now utilizing what was previously a dead cycle. If you look at the, I believe it's figure 4-17 in the textbook, pages 272 to 274. So if you look on page 274, you'll notice that our return micro instruction or sequence of micro instructions also has a dead cycle. And so what that means is if we merge our main, so if we, let's come up here, if we merge our main into the end of each microcode sequence, we're going to be getting some speed increase every time we call pop and every time we call return. This would be, of course, more helpful if we had a different micro program which had more dead cycles, but in our case, we're going to see some minimal speed improvements based on this. So in the next couple videos, we'll look at some other techniques that we can do in addition to this.